Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to cover Pure Maths 1 series, part 3, geometric progressions. In part 2 we covered arithmetic progressions. Now we want to move on to geometric progressions. So there are 3 formulas that go with geometric progressions. And again, I want to refer you to the formula sheet that Cambridge provides. And you can see right here, geometric series. Remember, series is just have adding in between the terms. And so you have your 3 formulas right across here in a row. So the 5 formulas that you're going to be using in series are 2 for arithmetic and 3 for geometric. Make sure you use your formula sheet, keep that handy so that you get used to using it. So here we have a subscript n, that is a specific term, the nth term. So n could be the first term, second term, third term, fourth term, fifth term, so on. So the specific term that you want to find in the sequence or the progression. Remember, sequence, progression, basically same thing. Series means you're just adding it up as you go. Then if you want to take the sum of the series up to a certain point, that would be your s to the n. So remember, your a1 is the first term. The r is what's called a common ratio. In arithmetic series, each term was separated by an addition or a subtraction called the common difference between the terms. Now with a geometric progression, it is going to be separated by a multiplication or a division of the same value between the terms, called the common ratio. So the sum of a specific number of terms has this formula here, and some curriculum will write this in the opposite direction. In other words, they'll write this as a1 times r to the n minus 1 and r minus 1. So the order doesn't really matter as long as you do it the same direction, top and bottom. So it can be 1 minus r to the n over 1 minus r, or it can be r to the n minus 1 and r minus 1. So you might see it either way, doesn't matter. And then we have the sum to, here's maybe the first time you might have been introduced to the infinity symbol. So the sum to infinity, that is, if you add up the terms basically forever and ever, it will equal a to the 1 divided by 1 minus r. Very interesting formula here. However, this can only work if the absolute value of the ratio, we put absolute value because your ratio can actually be positive or negative. If your ratio is negative, it means the sign of your terms alternate, positive, negative, positive, negative, positive, negative. So your ratio can be positive or negative. What's important is that the absolute value of the ratio has to be less than 1. If it is greater than 1, you cannot do a sum to infinity because your sum will go off to infinity. You won't get a particular finite value. But if your ratio is less than 1, if it's a fraction that's less than 1, then this sum to infinity will approach a particular value. We'll look at that a little bit later. So here are our definitions of the different variables. Again, notice there's quite a few variables. There's 1, 2, 3, 4 different variables here. 1, 2, just 3, 4 different variables there. Here's 1, 2, 3 different variables here, meaning there's a lot of ways these questions can be asked depending on which variable, what information they give you, and which variable they want you to find. So here again is the definition. Here's a couple of simple examples. Maybe if you had geometric series at some point back in IGCSE material, here would be a simple example. Here you're given a sequence, 3, 6, 12, 24, 48. So 3 is the first term. To find the ratio, you just take any two consecutive terms and you take the second one divided by the first one. Kind of like arithmetic progression, we took the second one minus the first one, the common difference. This is a common ratio. Take the second one, divide by the first one. So whether you go 6 divided by 3, you get a common ratio of 2, or whether 12 divided by 6, or whether 48 divided by 24, you still get a common ratio of 2. So here I put the word diverge because your ratio is greater than 1. So it's going to diverge, it's going to go away toward infinity. You'll never get a finite value to represent the sum of this progression. Then, and then again, n being your first term, second term, third term, whichever term of the progression that you want to look at specifically. Here's a different one, 8, 4, 2, 1, 1/2. Again, your specific term. Here is your first term, a to the 1, a subscript 1. And then again, to find the ratio, you take the second one divided by the first. Don't get into a habit of doing bigger minus smaller or bigger divided by smaller. That's not what you want to think. You want to think two consecutive terms, the higher term in terms of sequence, minus if it's arithmetic, or divided if it's geometric by the term right before it. So 4 divided by 8 is 1/2. If you do 1/2 divided by 1, still 1/2, or 2 divided by 4 is 1/2. So that's called the common ratio. Now, because this r is less than 1, the summation of this sequence, or if you're adding it, the series, will converge to a specific finite value. Okay, so we'll look at that in a minute. Here, let's look at our formulas in action. So if we want to find the fourth term, which we already can see our fourth term is right here, but if we want to find it, we take a to the 1, that is the first term that we're starting with, and then we take the ratio with n minus 1. Well, why is it n minus 1? Well, notice between 3 and 6 is one multiple of 2, between 6 and 12 is another multiple of 2, and between 12 and 24 is another multiple of 2. So from the first term until the fourth term, there are 3 multiples of 2. So that means we need to take n minus 1 factors of 2. So we have 3 times 2 to the 4 minus 1, which is same thing as 3 times 2 cubed. Now, be very careful to follow your order of operations. You cannot go 3 times 2 is 6. You have to do exponent before you do coefficient. So be careful that you follow the order of operations. Exponents come before multiplication. So sometimes, and that's why I put the 2 in parentheses, so that you recognize that this 2 has to follow the exponent first before you multiply. You cannot go 3 times 2 is 6 and then raise it to the exponent 3. So always in algebra, be mindful of your order of operations. So this is a 2 cubed, which becomes 8. 3 times 8 is 24, and you can see that 24 is the correct answer. And if we want to sum the first 3 terms, here we can already see the sum of the 3 terms here is 12 plus 6 is 18, 19, 20, 21. We can see we're going to get 21. So here's the sum formula. The first term, a, times parentheses 1 minus r cubed. Now this time it's just n, not n minus 1. 1 minus r cubed over 1 minus the r, 2. So 1 minus 2 is negative 1. Don't worry about the negative. In fact, that's sometimes why if I do the formula, I sometimes switch it and put r to the n minus 1 and r minus 1 because I like to end up with a positive on the bottom. Doesn't matter. Don't worry about the negative. 1 minus 8 is a negative 7. The negatives cancel, and you end up with a positive 21. Now, if your numbers were negative, then your sum will end up being negative as well. So don't worry. Just make sure you're careful with the signs and pay attention to those. So we see that we get 21 and 12 and 6 is 18 and 3 is 21. Then if we want to do the sum to infinity, we cannot do the sum to infinity for this series up here because it diverges. Our ratio is greater than 1. Obviously, if you multiply by a number greater than 1, it continues to get bigger. But if we multiply by a value less than 1, then it means we keep adding a smaller, smaller, smaller value. So at first, this might seem a little crazy, but here we have 8 plus 4 plus 2 plus 1 plus 1/2, and then half of that's 1/4, 1/8, 1/16, 1/32, 1/64, 1/128, so on, so on, so on, so on, forever and ever and ever and ever. And if we add all those up, it's only going to come to 16. Okay, so here we have our sum to infinity, our first term 8 divided by 1 minus the r. So 1 minus 1/2 is 1/2. 8 divided by 1/2 is 16. Now, you might like, really? You're going to add up all those numbers and it only comes up to 16? The first number is half of that. It's already 8 plus 4, that's already 12. That means all these numbers can only add up to 4. 8, 12. Now we already have 14. Here we already have 15. We're only 4 numbers into this infinite series and we're already to 15. But the thing is, we keep adding a smaller and smaller value. If you were to see a curve of it, the curve would go up very steep at first and then it goes off like that. And so what you're doing is you're approaching a particular value. So you can see that 8 gets you halfway there already. But as you get up here like we said 15, so this is now 15.5. Then you add a quarter. Well, now you're at 15.75. Then you add an eighth. Then you add a 16th. So what happens is, as you get way up here fast, you get up to 15, 15.5, 15.75, and eventually it becomes 15.99, 15.9999, 15.999999, and it continues just being 15 point, and you get a longer stretch of 9s following it, but it will never increase higher than that. It just is a higher number of 15, but never reaches 16. So since this becomes 15.999 indefinitely, because we're adding indefinite number of values to it, when we round that, of course, 15.999999 simply becomes 16 to whether you're dealing with 2 significant figures, 3 significant figures, however many significant figures really you want other than just 1, and you get 16. So this has an importance you're going to see when we're dealing with either maximum values that a series can attain as far as adding them up. Okay, so here's a basic overview. So we're going to start with our examples, and what I'm going to do is I'm going to use the exact same examples that we used in part 2 with the arithmetic series, but after the arithmetic question, they then continued with like a part B with the geometric question. So we use the same ones so that if you're following along in your work, you can just continue the question and see the difference between arithmetic and geometric for that. So let me set up the first one. Again, I'm going to erase the formulas. I don't want you looking at my board or at the video for formulas. I want you to follow along in your formula sheet so that you get comfortable with using it. Okay, here's our first example. And just in case you forget, let me share screen so that you can see what we did yesterday. And here's the question that we had yesterday, or in the part 2. And it said, it said in the part 2 arithmetic progression, it says part A, in an arithmetic progression, the sum of the first 10 terms, and we did that. We showed that the common difference was 1/3 A. Maybe you remember that problem. And then we did the part II, given that the 10th term is 36 more than the 4th, find the value of A. So that was all about arithmetic. Now the question continues to part B, and this is where we're at now. It says the sum to infinity of a geometric progression is 9 times the sum of the first 4 terms. Given that the first term is 12, find the value of the 5th term. So let's go back to our board here and see that we've identified, first of all, that we've changed now to geometric progression. So pay attention to the questions, whether you're in arithmetic or geometric. Like I said, in part 4, we're going to go to where they're actually combined in the same problem. And then it gives you an equation. It says that the sum to infinity of the geometric progression is, that's your equal sign, 9 times the sum of the first 4 terms. The first term is 12. Find our 5th term. So here's the information that we pull. Remember, again, you got to be able to read the English, pull out the information into a mathematical meaning, and then make sure you find your verb. What is it exactly that we're supposed to do? So it says find the 5th term, but we can't use our A to the N formula because we don't have the R yet. So in order to get the R, we're going to have to work with this equation. So we start with our sum to infinity, which is A1 over 1 minus R. There's our formula for sum to infinity with the information that we have available, equals 9 times the sum of 1 to 4. So the sum of 1 to 4 is first A1 times 1 minus R to the N. Well, our N is 4 over 1 minus R. Okay, so in the parenthesis here, if we expand the parenthesis all the way down to here, in this big parenthesis is our sum to 4 terms, and outside is this 9 times that. Okay, so this looks a little complicated, but if you just take your time and remember that we want to get rid of fractions first, so if we multiply by 1 minus R to both sides, that will cancel out our fractions. So no more fractions here. So now we have a 12 equals 9 times 12 times a 1 minus R to the 4th power. So if we divide everything by 12, divide by 12, divide by 12, here we see this cancels. Now this is not 0. Anything divided by itself is 1, equals 9 times 1 minus R to the 4. Divide by 9 here. So just take your time, follow your order of operations, or in this case, the kind of the opposite of the order of operations to get the R by itself. Remember, we're trying to find R. And so we get 1/9 equals 1 minus R to the 4th. So if we bring this up here, if we add this R to the 4th over here and subtract the 1/9, R to the 4th equals 1 minus 1/9. R to the 4th equals 8/9. Now you might want to be tempted to fourth root both sides to get the R. You can, but you might want to wait. The reason why I say wait is the fourth root of 8/9, you're going to put it into your calculator and change it into a decimal. You don't really want decimals halfway through the problem. We don't want to round anything until we get to our final answer. So it's best to just leave it like this, or you can even leave it like this. We don't really understand what this R to the fourth is yet, but there's no need to rush it forward. We say we need to find R. Well, we do have R already as the subject. We're just not sure what to do with the fourth. Do we want this or do we want this? So just be patient and see what you need to do with the R. Now that we have R, let's look and see what our A to the fifth looks like. So our A to the fifth is A1 times our R to the n minus 1. Well, this is 5, so 5 minus 1. Well, that means we want 12R to the fourth. What do you know? R to the fourth is actually what we want, not just R. So if you had went ahead and put it like this, it's okay, but don't turn it to decimal yet. You can always look back in your work and hopefully part of correlating information. Oh, I've seen R to the 4 before. It's right here. So this just becomes 12 times 8/9. So here we can see a little bit of simplification here. Divide by 3, divide by 3. So 4 times 8 is 32/3, which equals 10 2/3. Or if you changed it into decimal at that point, that's 10.666. It would be 10.7 to 3 significant figures. Okay, so this then would be our answer. Actually, any one of these three forms would be fine, although this is an improper fraction, so maybe they might prefer the mixed number, 10 2/3, or the decimal to 3 significant figures. Both of those would be acceptable. So here we continued on with our geometric. Again, look for those equations that they provide for you. They're not your formula equations. They're relationships between information. So use that algebraically, pay attention to the signs and orders of operations as you go through. So let's look at the second one that we did in part 2 and continue it on into the geometric progressions. Okay, here's our second question. And again, let's go to screen sharing so that we can see what the question was that we looked at in part 2. Remember the 21-day period, and we see that she runs each day increases by 1.2. So that means you're adding 1.2 every day. It's arithmetic. It doesn't say arithmetic. You have to figure it out from the question. Then we move down here to find the total distance. Then we get to part B. Now it calls it a geometric progression. So again, you want to identify that change from arithmetic to geometric. It says that the first, second, and third terms, so first, second, and third, are x, x minus 3, and x minus 5 respectively. Find the value of x. So here's our question, find x. So as you go through the question, let's get back to our board. As you go through the question, underline important things. Again, it's geometric. So first, second, and third, here's our first, second, and third terms of the progression. So that's important. And again, our verb, we're trying to find x. Now, it's difficult to use any of the formulas because we have all these unknowns. But remember that with geometric, there's a common ratio, meaning any two consecutive values, you divide the higher one by the lower one, not the higher value, but the higher sequence number by the lower sequence number, and that is the common ratio. But it's the same thing for any consecutive values. So we can use 1 and 2. We can also use 2 and 3. So what we can do is we can create for ourselves a proportion. X minus 3 over x is the common ratio between the first and second term. But it is also the common ratio between the second and third term. As long as they are consecutive terms, the ratio will be the same. So x minus 5 over x minus 3. So again, you cross multiply, you get an x minus 3 squared. This one times this one equals x times x minus 5. When you multiply that out, you get x squared minus 6x plus 9 equals x squared minus 5x. So as you start to simplify, if you subtract x squared from both sides, it cancels out. If you add 6x to the other side, you end up with x equals 9. So here we have x equals 9. We now have the value of x. So if we want to, we can go back and establish our geometric progression. So we have a 9. 9 minus 3 is 6. And 9 minus 5 is 4. Okay, so 9, 9 minus 3, 9 minus 5. Here are our first 3 terms of the progression. And if we want to find the ratio, all we need to do is divide. So our ratio is 6 over 9, which equals 2/3. Now, why am I doing the extra work? Well, we need to go back to the problem and see what the next part is. So screen share here again. And here we found x. Now let's go down here to part I. Find the fourth term of the progression. So find A4, the fourth term of the progression. And so let's go back again to our board here. So we circle our verb, find a to the fourth. We now have our r, or because we found x, we can establish the progression and we can find the r. Now it's just a matter of following the formula. So a to the fourth equals a1, which now we know is 9, times r, which is 2/3, raised to the 4 minus 1 power, is 9 times 2/3 cubed. Again, make sure you're doing exponents before multiplication. You cannot cancel the 3 and the 9. Exponents before multiplication. Follow your order of operations. That's probably a very common mistake, unfortunately, for A-level students, is simple mistakes like order of operations. By now, you need to eliminate those kind of mistakes from your work. So now we get 9 times 2 cubed is 8, 3 cubed is 27. Now you can simplify, divide by 3, divide by 3. If you divide by 3, you get, or this divide by 9 and you get 3 and you get 1. So you end up with 8/3 as your fourth term. Now, actually, there was another way that you could do this. I followed you through with the formula from your worksheet. But remember, being efficient at math is also about correlating information. We already had term 1, term 2, and term 3. In other words, to get our term 4, all we have to do is multiply by another ratio. Here's common ratio 1, here's common ratio 2, here's common ratio number 3. So really all we had to do is take 4 times 2/3. That is the third term. To get the fourth term, we just multiply it by one more ratio and you get 8/3. Same answer, but this is more efficient because it shows that you're correlating information at a faster rate. You're not just doing math. You're not just following formulas. You're understanding relationships between information. That's what's key in Cambridge type testing, is to make those mental correlations, and that's what you want to develop in your skill set. Your math skills should already be developed by now, or you wouldn't be in A-level math. Okay, so it's more than just doing a formula. It's thinking about what you're doing. It's not saying you can't do this. You still get the right answer. It's still okay, but you should also recognize this. Okay, so let's move on to the last example. Again, it will be from what we did in part 2 and then doing the geometric part. Okay, here's our last example. And remember our boxer scenario that we had back in part 2, arithmetic series. Let's take a look at that again. So let me screen share so that we can look at the problem. Said 2 heavyweight boxers decide that they would be more successful if they competed in a lower weight class. For each boxer, this would require a total weight loss of 13 kilograms. So that's the target. At the end of the week, they each have recorded a weight loss of 1 kg. So we get this from the information that's at the beginning that applies to everything below. And they both find that in each of the following weeks, their weight loss is slightly less than the week before. So in part 2, we dealt with boxer A, whose weight loss followed an arithmetic progression. And so we did part I and we did part II. Now we move on to the part III. Notice there's a heading over it, meaning this information now applies to part 3. It says boxer B's weight loss in week 2, I put it over here, is 0.92. Now remember, we already saw that both of them in week 1 lost 1 kilogram. So I wrote that information again because it didn't give us week 1 here. We have to look at the top. And it says the weight loss follows a geometric progression. So that's important. And then we get into part II, says calculate the total weight loss after 20 weeks and show that he can never reach his target. So let's get back to the board here. And we see again, taking out the important information from the English into mathematical situation. So we have boxer B, geometric progression. I added week 1 again because it didn't repeat the information. I had to go back to the top. Week 1 lost 1 kg. Week 2 lost 0.92. So that means our progression follows 1.92 ... We only have 2 values for our progression, but really that's all we need to find the ratio. The ratio is going to be 0.92 divided by 1, which is just 0.92. So we've established the ratio in the geometric series. And then we look at the verbs. What are we supposed to do? Calculate total loss, that's a summation formula, with for after, or basically at the end of the 20 weeks. So that's the N in the summation. And be careful that you read the full question. Sometimes students don't read the whole question. It just says calculate and they start doing it and they forget to do the rest of the problem. Read the entire problem, circle those verbs so that when you're doing your work, you realize there's another part to the answer you need. So show that you can never reach our target. And our target, again, I repeat the information. It didn't tell us, it just says the target. Go back to the top, it says 13 kg is how much they wanted to lose. So we want to demonstrate that even though he keeps losing weight, he'll never reach 13. That's interesting. So let's calculate first how much weight he loses after 20 weeks. Remember Boxer A from part 2? He reached 13 kilograms in 16 weeks. Remember that? Well, now Boxer B is losing by a geometric series instead of arithmetically the same amount every day. It's slightly less every day. So let's see how much he loses after 20 weeks. So the sum for 20 is A1, which is 1, times 1 minus R to the 20th power. Remember, for summation, it's not n minus 1. It's just n over 1 minus R. So we can make this a little bigger here. This, so A, 1 minus R to the n over 1 minus R. Now, because this is decimals and exponents, you might as well just go ahead and do that in your calculator. And when you do that in your calculator, you're going to get the answer 10.14. So don't just trust my math. You should always double check what I do. I can make mistakes as well. Plug it in your calculator. Make sure that this is what you get. And so I wrote down 2 decimal points. We only need 3 significant figures. So this would be, our answer would be 10.1 kg, and this is to 3 significant figures. Okay, so that's our answer for calculation. So after 20 weeks, Boxer B has only lost 10 kilograms of weight, whereas Boxer A, with an arithmetic progression, lost 13 kilograms by week 16 and had the potential to actually lose more weight, as we saw in the graph. So here is, after 20 weeks, only lost 10 kilograms. Now we need to show that it never reaches the target. This idea of a maximum value or not reaching the target is implying adding up to infinity. If this is a geometric progression, and if our R is less than 1, which it is, 0.92, it means we can add continually. So if this boxer were to continue to lose weight indefinitely every week after week after week after week, we can come up with a sum to infinity. And we get a to the 1, which is 1, over 1 minus R. So you get 1 over 0.08. And when you put that in your calculator, 1 divided by 0.08, you get 12.5. That means 12.5 kg is the maximum amount of weight that this boxer is going to lose with this particular routine that he's following. So remember again, the graph goes up steeply at first, but then tapers off towards a limit. Gets closer and closer and closer without ever reaching the value. And the limit for this is 12.5, and he wants to reach 13, which is even higher than that, half a kilogram higher. But he'll never reach his target no matter how long he's on this particular weight loss plan. So maybe he needs to change his plan. But here you can see, again, you got to understand the English, not reaching the target or finding a maximum value is associated with our sum to infinity. So here's been 3 different examples. All of them continued from the arithmetic that we covered in part 2. So in the next video, part 4, we're going to look at questions that actually integrate them together in the same question. They're not integrated in the same series, but taking an arithmetic series and a geometric series and then asking questions that relate the two of those. So it's going to be more challenging, more interesting, and more fun. So thanks again for joining me in the Zoom room. See you again next time.